Hello, this presentation is about organic chemistry laboratory experiment of tetraphenylcyclopentadienone. It is a dark purple to a black crystalline organic compound that has a melting point around 220 degrees Celsius. In this experiment, synthesis of tetraphenylcyclopentadienone will be conducted via aldol condensation. Aldol condensation provides a good way to form a carbon-carbon bond. It includes addition and subsequent dehydration steps. In addition reaction, carbonyl sources such as two aldehydes to ketones or an aldehyde and a ketone can react. An addition reaction results in a beta hydroxyaldehyde or a beta hydroxyketone depending on the starting materials. The subsequent dehydration gives a conjugated enone or in another name, an alpha-beta unsaturated aldehyde or ketone. Naming as a ketol condensation product could have been preferred instead of aldol. However, because the reaction was initially developed with the aldehydes, the name aldol was coined and has been applied to both reactions that form it and form unsaturated ketones as well. In the aldol condensation, one of the carbonyl compounds mentioned in the previous slide acts as an enol or enolate. Enolates are organic anions formed by the deprotonation of alpha carbon of carbonyl compounds. As a reminder, alpha carbon is the carbon next to the carbonyl. Their names themselves actually reveal their double functionated structures. For example, N in enol refers to a double bond as in alkene, while ol refers to a hydroxyl as in alcohols. The formation of an enol or enolate depends on what presents in the medium as the catalyst. Is it acid or base? So both the enol and the enolate can be derived from the same carbonyl compound. On the right top corner, enol formation from a ketone is shown in the presence of acid. On the other hand, enolate formation from an ester in the presence of a strong base is demonstrated on the left bottom corner. We can see that enolate is the deprotonated form of enol. By choosing a bulky base such as lithium diisopropylamide, we can produce enolates selectively because it will only remove the proton from the less hindered carbon in an unsymmetrical carbonyl compound. We can summarize that the aldol condensation involves three primary steps in the mechanism. First, the formation of an enol or enolate anion, and second, the reaction of that enol enolate with another carbonyl group, and finally, proton transfer and dehydration. Although reactions are highly reversible, control of reaction temperature is critical because high temperatures promote aldol condensation. A cross-aldol addition reaction generally involves one aldehyde or ketone without alpha hydrogens and one with alpha hydrogens. Therefore, only the compound with alpha hydrogens can form an enolate in the base. If both compounds contain alpha hydrogens, then multiple products would be produced. However, if there is no alpha proton on any of these carbonyl compounds, there will be no enolate formation, so will be no aldol condensation. After this explanation, what would you expect from this experiment? Multiple products or one product? Can you explain? Maybe after having a look at the reaction mechanism, you will have more ideas to answer this. Reaction mechanism. In this experiment, we will perform an aldol condensation which involves one ketone that has alpha hydrogen atoms. This one is dibenzyl ketone, and one that does not, and that one is benzyl. Thus, dibenzyl ketone will serve as a nucleophile because it will donate protons to a base to form an enolate. This aldol condensation reaction starts with the typical enolate formation. The explicitly shown protons on alpha carbons are the most acidic on dibenzyl ketone. Most alkane protons have a pK around 40 to 50, so they are not acidic at all. However, the protons on the carbon, alpha to carbonyl, have a pK of around 19, so there's a difference of at least 20 pK units, a dramatic difference in the acidity. Why might that be? Let's answer this through the end of this slide. In the first step, hydroxyl removes a proton from the alpha carbon on the dibenzyl ketone. You can see the formed enolate and its resonance structure in the figure. And this is also the answer to the question I just asked. Because enolate, the conjugate base formed after deprotonation, can be resonance stabilized between the anion on the carbon and the anion on the oxygen atom. That's why alpha hydrogen is so much more of an acidic proton. This analyte is now ready for a nucleophilic attack on the benzene. As of now, I will abbreviate the phenyl groups as pH to save some room on the next mechanism slide. This reaction mechanism includes two overall aldol condensation that repeats itself. For the flow of the reaction, you can follow the little blue arrow that will appear on top of the compounds in the figure. When the enolate attacks the carbon of carbonyl, the double bond on the carbonyl moves onto the oxygen, making it negatively charged. Then a proton transfer takes place from the hydrogen of the water to this oxygen, converting it to a hydroxyl group. Besides protonation, deprotonation occurs and the structure loses alpha hydrogen. The formed intermediate is called beta-hydroxyketone, which is also given as aldol intermediate A in the figure. This step concludes the aldol addition of the overall first aldol condensation. Aldol intermediate easily loses hydroxyl because pi-electron conjugation, heat, and the anti-periplanar conformation enable it to live without protonation that converts it to the water. The hydroxyl loss causes another enolate formation with a highly conjugated system, the aldol intermediate B. This is the condensation step in the overall first aldol condensation. After that, step 1 and step 2 repeat. Namely, alpha hydrogen is deprotonated and another nucleophilic attack occurs. But this time, the nucleophilic carbon on the enolate is exactly 4 carbons away from the other carbonyl carbon on the compound. This leads to forming a stable 5-membered ring. Thus, intramolecular aldol condensation occurs here. The oxide grabs a proton and turns into a hydroxy. This causes again the hydrogen staying between a carbonyl group and the carbon attached to a hydroxyl to be quite acidic. As the thumb of the rule, acidic protons are removed in the presence of a base. A base comes in yet again to take that acidic proton. With that, the second beta-hydroxyketone intermediate is formed. This step concludes the second aldol addition, and after that, the same elimination of hydroxide occurs. This yields the dienone product, tetraphenylcyclopentadienone. Procedure. Start the experiment by adding 1.5 gram of each dibenzyl ketone and benzyl and 12 ml absolute ethanol into 50 ml round bottom flask. It is critical to prevent water from coming into contact with the reactants. Attach the condenser to the round bottom flask and prepare a hot water bath at 70 Celsius. Do not forget to clamp the condenser to the ring stand. Please notice how the condenser is assembled in the picture. It's important to connect water hoses to the condenser accordingly so that the water flows against gravity by going in the bottom of the condenser and out the top, or else the condenser will not be effective as it will not fill completely. Then raise the temperature to about 80 Celsius while continuing to stir the mixture. During this time, try not to overlook the reflex ring. It is seen roughly 1/3 of the way up the condenser. A reflex ring is the upper limit of where hot vapors actively condense. If you notice it is further away than 1/3 of the way up the condenser, you need to lower the temperature of the heater right away. Use a Pasteur pipette and a dropwise 2.25 ml of ethanolic potassium hydroxide solution downward through the condenser into the flask. The mixture will immediately turn deep purple, which shows that the reaction takes place very fast. Raise the temperature of the hot bath to around 85 Celsius and heat it with stirring for 15 minutes. As a reminder, never insert a thermometer on top of the condenser or else the flow of the vapor is blocked, and this may cause an unexpected vapor pressure constitution in the system. After 15 minutes heating, remove the flask from the hot plate and leave it cool to room temperature. Then immerse the flask in an ice water bath for 5 minutes. Do the vacuum filtration by washing the deep purple crystals with 3-4 ml portions of cold 95% ethanol. Ethanol is the rinse solvent, and it can also be used in transferring crystals from the round bottom flask to the Buchner funnel. Then dry the product in the oven for 15 minutes and weigh the dried product to calculate percentage yield. Finally, determine the melting point of your product